Hey guys, in this tutorial we're going to take a look at tensile structures. We're going to sort of look at something similar to the Frei Otto German Pavillion. Just to show you, this is the simulation that we're going to be running in Kangaroo. Plug in for Grasshopper, which is going to create a mesh intention. Alright, cool. So that's the end result. We're going to go ahead and recreate it now. So I'm going to start by building that sort of spiral shape that we had, and I use this method every now and again. We're going to start with two expressions to form a parametric equation, and the equation is going to be a times t times sine of t, and the other equation is going to be a times t times cosine of t. So if you take sine of t and cosine of t for a defined range between 0 to 2 pi, what you will get is a circle. I've explained that in previous tutorials. But if we have our t over here as well as outside the call to the sine function, what you can do is you can create an incremental sort of increase, which is how we get the spiral sort of shape. So that's what I'm going to do now. I'm going to create a range, and I'm going to make it a multiplier of pi for my domain, and I'm going to plug in a slider which is going to have a maximum value of 6, which would give me 3 full rotations because that's 3 times 2 pi, but for the moment I'm good with this. And so I'm going to plug that into my... oh, I actually haven't relabeled these yet. So this is going to be T, and this is going to be A. And same thing here, this is T, and I'm going to add A up here. Cool, so now I'm also going to throw down some sliders. Oh, actually just one more slider with the maximum value of 100 for my amplitude. And actually we do need one more slider, which is going to be an integer slider, and this one is going to control our number of divisions. Alright, so now we need to put down a construct point node, and this is our x component, and this is our y component. So you can see as we increase this, we're getting more and more, well, like a greater sort of portion of a spiral. So what I'm going to do now is I'm going to put an interpolate curve through here, which is going to give me well, an interpolated curve through these points. And then what I'm also going to do is I'm going to take a curve closest point. There we go, curve closest point. And what I want to find is the parameter, whoops, I want to find the parameter at which each of these points exists on this curve, so that I can get, if I do a evaluate curve, what I can get is a parameter over here which will correspond with these points, and this gives me a tangent vector. Actually, instead of doing a curve evaluate, I might just see how my perpendicular frame works. Sometimes this can be just about what we need. So what I'm looking for here is that all my x directions are lining up, and you can see we do have an issue here where this one is facing the wrong way, so I don't like that. That's not going to work for me. So I'm going to see if my curve evaluate does any better than that. So this tangent vector is not quite what we want, because a tangent is basically, well, a tangent would form a line going straight across like this at this point, because a tangent is sort of how do you explain a tangent? A tangent is the direction in which that curve is heading at that specific moment, whereas what we want is the normal vector, the vector pointing directly straight outwards. So all we need to do is we need to rotate that vector. So I'm going to take my vector here and I'm going to rotate it along the z-axis, and I just need an angle. I'm not going to plug in a slider for this because this is going to be fixed. It's going to be 0.5 times pi, which is a quarter of a rotation. And now I'm going to create a linear array of this collection of points along this direction. And there we go. That's what I wanted. This is giving me well, yeah, this is really good. So now I've got a sort of a uniform distance offset along each of these curves with a whole lot of points. So now I can increase. Okay, so my direction on my distance between these points is a little bit small. So what I will do is I will throw down a multiplier here. Thing to note, if I haven't explained this before, is vector amplitude and multiplication do the exact same thing. It does not matter which one you use. And for whatever reason, I prefer to use a multiplication. I don't know, maybe it makes me feel like I know Grasshopper a bit better. But you can see if I plug this in here, and I do the same with this, it'll do the exact same thing. And that's because this tangent vector that I've extracted is a unit vector, meaning that the vector has a vector length value of 1 units. Whereas this amplitude here, if I were to take this vector length, whoops, can't spell properly. If I were to take this vector length and pull out a panel, we could see that it's always going to equal 3.877. Whereas, let's say if I were to take this vector here and then multiply it again, and then put it through my vector length, it's going to be 3.877 squared. So yeah, that's why this multiplication works. And you know what? As long as you're using unit vectors, they're exactly the same thing. So I'm going to stick with my multiplication. All right, so that was a little bit of a tangent, but now we're good to continue. So we've got the base points for our for the configuration of our mesh. So I'm gonna now use a mesh from points component, and oops, not that. Mesh from points. So I'm going to plug this in here. The mesh from points component, if you do not have it, I say this every single time I use the component because I always get questions about this. The mesh from points component is it's a plugin called MeshEdit, or it's called Otto. You can find it on the Food for Rhino website. I'll probably put a link to it in the description as well. Get it, it is super useful. Cool, so in order to create this mesh from points, we need to flatten this input, and we need a number of U and V divisions. So our U divisions, I believe, are going to be this number here plus 1. And I'm just going to change this to U, and then I'll drag it over here and plug it in. And now my V divisions are going to be the number of elements in the linear array over here. So I'm going to create a slider so that I have control over this. And I'll make it an integer slider with a maximum value of 20. Plug that in. And I do not need to do V plus 1 for this direction. Cool, so there's our mesh. we can preview this off, and I can just increase that a touch. So I'm happy with that. That's at this stage. Apart from one thing, I do feel like I want a bit of elevation in my Z direction, so that this is not just a completely planar mesh at the moment, and that will change my my tangent vector a little bit, but I'll probably still be alright with it. So we're gonna put a multiplication down, and we're going to multiply this range value coming out, probably with a maximum value of 100, and we'll plug that into my Z, and yeah, something like that works for me. So you can see this point stays fixed here, but this one moves up a little bit, and you know what, I'm not too bothered by that, so I'm going to keep it like that. Alright. So now we can get into the Kangaroo side of things once we've built this mesh. So, like I talked about in my previous tutorial, anytime you're using Kangaroo, you need to put down the Kangaroo solver, which you access from Kangaroo here, Kangaroo physics. And so our mesh goes into geometry, and now we need to start setting up the rest of it. So our force objects is the first thing I like to set up. And so for this, we're going to use springs from line. And so the springs from line asks for a connection. I'm going to get my Weaverbird mesh edges. I'm going to plug that in. And so the connection is just a line between 2 points. So now that's gone, that's turned from orange to white, indicating that that is now working properly. So we can now plug that into our force object. I'm also going to insert a Unary Force, and the points for my Unary Force are going to come from my mesh from points. I'm going to deconstruct the mesh, and that'll give me my collection of vertices, and then I just need to plug in a force, which is a vector in any given direction. We're going to be using gravity, so I'm more than happy to keep that as a z vector, and I'm going to give this a maximum value of 100 and a minimum value of negative 100. This is just a personal preference thing. I always like my gravity value when it's going downwards to be positive. You don't need to do that. You can just have, like, if you just plugged negative 100 in, that would be your direction of gravity, but personal preference, as I said. Alright, so now our Unary Force can also go into the springs, into the force objects along with the springs, and now we can begin to test the simulation. We've got force objects in geometry, so we can see what happens. You can use either a button or a Boolean toggle. I prefer to use a button, and you're going to notice that it throws an error, and that's because key thing that I really want to reiterate with these tutorials is your force objects have to be flattened. It's just a convention of how Kangaroo for Grasshopper works. Alright, so now when we press the button, it will reset our simulation, and we're good to go. I also need a timer, and this is going to make sure that my simulation continues to update. So I'm going to set the interval to 20 milliseconds, and you can see we are getting a very strange result. I might just set this back to 0 for now, and reset the simulation so we can kind of see what's going on. So the issue that we're having is that, well, our springs have a rest length of 0, meaning that they're trying to tend to absolute tensility. I believe that's the right word, yeah. So what we need is we need a curve length value over here. So I'm going to take this curve length, and if I were to plug this into my rest length, well, immediately that's going to do something quite strange. But if I reset the sim and let it go again, you can see nothing's happening because now they're at a rest length of what their length already is. So then now I can take this rest length and I can multiply it by a slider. So I'm gonna, yes, multiply it by a slider. So we'll set it to 1, plug it in, and just quickly realign everything. And now as soon as I change this, we should see our mesh begin to shrink. At 0, it starts to do the same thing that it was doing before, and if we put it back up to 1, it implodes on itself, which is not ideal, but that's kind of what's going to happen. Alright, so now for this next part of the simulation, I'm going to show you 2 ways how to do it. I'm going to show you how you could do it just in Rhino, and then I'm going to show you how you could do it so that it remains completely parametric. Alright, so what we're going to do is we're going to extract the points from this deconstruct mesh component, and I'm going to bake them out. And so then when I preview them off and preview this off, let me also just grab a mesh output for this geometry out on this side and preview this off. It is going to give us a collection of points for all these for this mesh. So what we can do is we can plug in some anchor points. So I'll just make a copy of this point node here, and I'm going to start to tell it which points I want to be fixed. So maybe I'll select around these points here. Oh wait, I don't quite like how I did that. I'll select this one, this one, this one, here, here. I'm just making a selection at the moment. Be pretty rough with it. Here, here, and cool. So those are going to be our anchor points. I'm also going to set a few anchor points for my middle. So I'm going to set this one, 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 you, and you. Alright. So now I can plug these into my anchor points. And if we were to now take down our rest length, you can see we start to get a bit of tension in the mesh. Anywhere that we've got an anchor point, it's going to hold. So what we could do with this as well is we could start to pick some of these points that we had for our anchors. This one and this one, and when we move them up, our mesh is going to react accordingly, which is a really cool thing. That that Kangaroo does. And now I might just add a bit more gravity into this so that we're getting a bit more sort of realistic behavior from the simulation. And yeah, we can once again move these around. We could move around some of these edge ones too. Notice all these ones that I've selected that aren't part of the simulation aren't going to affect it at all. But yeah, we can interactively come in and mess around with these. Now that's all well and good, but the reason I have a problem with this is because as soon as we reset this simulation, all these points that we have here have, well, they've, should we say, they've sort of lost their stickiness to the mesh, their mesh index, if you will. So they, even though we're referencing them in as anchor points, and they were in that original location, they no longer have any influence over the mesh. You can see as well, the ones that we moved on this side, they don't do anything anymore. So, I mean, you could sort of bring your mesh points back to where they were, and then start the simulation again, and you'll have all that feedback back. But, you know, I prefer not to do that. I'm going to show you how we can sort of extract that information to build it into the Grasshopper definition so that this doesn't happen. I'm going to remove all these points, and our mesh is going to start to do something funky again. So I'm going to delete this, and I'm going to pause the simulation. And what I'm going to do is I'm going to preview all of this stuff off that I don't need. And I'm just going to move this all forward so that we've got a bit of space to work with. So now I'm going to, firstly I'm going to take my naked boundary of this mesh, and that's going to give me a curve right around the perimeter, and then I'm going to explode it. And what we're going to do is we're going to take these points and we're going to run them through a Cull Pattern. And so my pattern is going to be true, false, false, false. Set that to multi-line data, and we should now get a result. So I also need to turn off this first list of points over here somewhere. Alright, so there we go. So these would all now be our new anchors. Key thing to note with this sort of approach is that like sometimes you might not get these corner ones in, and that's sort of something you just need to balance between the length of this list here corresponding with your number of steps. So it needs to be a sort of an equal multiplier. So 42 steps means I'm going to get 43 points. So what I actually need is this to be maybe 44. Oh, okay. It looks like we might be a little bit off with our divisions along this axis as well. So let me just correct that too. There you go. You can see when I get to 13, we get a point. Well, we get these two corner points, which is where our mesh starts from. And then if we were to go back here and adjust this, there we go. Now we're getting all those corner pieces in. Alright, so now the next thing I'm going to do is I want to pull out a sort of a ring of faces on the inside. So what I'm going to do is I'm going to do a mesh explode. I'm going to explode this mesh from points over here, which is going to give me all my individual faces, and then I'm going to do a partition list. And my size of my partitions, I'm not sure which collection I want at the moment. I'm going to try this one here, my V partitions, and then we can just test whether that's working or not with a list item. No, it's not quite. We'll try our V. Nope, still not quite. Okay, it looks like we're close here, but we might need to do, pardon me, let's try x minus 1. There we go. So, yes, of course. So we'll have, if we have, from our linear array, if we have 13 points, that's going to result in 12 mesh faces. So, yeah, that makes sense. Should have thought of that. So now we have our list item, and I'm also going to parametrically extract the sort of central face loop. And the way I'm going to do that is by creating another expression, and this expression is going to be the floor of x over 2. So this is taking the or the sort of limit of the amount of points we have, and then dividing that by 2 and finding the or rounding it to its lowest integer. And let me just remove these, pardon me, and then I'll plug that into my list item, and you can see we get that middle row of faces. So now I'm going to flatten this, and I'm going to use a Weaverbird join. Weaverbird is another custom Grasshopper component. I don't, as far as I'm aware, the last time I downloaded Weaverbird, you do not get it from Food for Rhino. You get it from the Rhino website, I think. I'm not entirely sure, but I'll post a link. Otherwise, you can just Google Weaverbird and you should be able to find a link pretty easily. Anyway, slight tangent there. So now we've got our ring of faces on the inside. What I'm going to do is I'm going to take the naked boundary of that again. And I can't quite tell what it's giving me at the moment, so I'll just preview all of this off. And there we go. So that is what we want. You know, I'll just keep this preview off while I'm doing this. And so we're almost there. All I want to do is I want to extract sort of one line. Well, like, oh yes, one edge loop, not one face loop. So I'm going to explode this polyline, and I'm going to take a list item, and this list item is going to be, let's see, I think it will be based on a series of this count here, u+1. Yep, so there we go. There's our oh. I mean, it has given us one point that we don't want, so we could probably just insert a tiny little expression here to fix this. I'll just put a slider down here, and so it's either going to be -1 or +1. Okay, there we go. So that's fixed it now. We now have a collection of points which correspond to our, well, sort of the center point, yeah, the middle of our mesh. So now I can preview this off, and I can use another culling pattern, because obviously we don't want all of these edges. And I'm just pulling that out in case I wanted to have a different culling pattern for that. But now we've got our collections of points that we're going to plug into our anchor points. So it looks like I didn't need as much space as I thought I did. I'm going to I'm going to plug these points into my anchor points here straight away, because those ones I do not want to move. And these ones I'm going to put through a move component. And so this move component needs to have a z vector for its input and a slider for that z vector. And that'll go up to, I don't know, maybe 100. Like I said, there's not really any sort of fixed parameters for this. So now we can plug these points straight into here as well. And when we reset the simulation, turn our mesh on, and enable it, we should see a result. I'll move this up, and there we go. We're now getting a good result out of our mesh. And so, okay, so now, I mean, we're almost there, but you can see as soon as I reset the simulation again, once again we lose any sort of contact between these points and the mesh. So there is one more thing that I can do, and it involves this button. I've talked about this in a previous tutorial, but what we have with a button or a Boolean value is either a true or a false, and that can also be interpreted, if we were to plug this into an integer, as either a 0 or a 1. And so what we can in fact use is this button as a multiplier, which sort of tells us whether to move the geometry or not. So I can put a multiplier down here, and I can multiply this result here, except, okay, so at the moment, when the simulation is running, it's giving me false, which means it's going to multiply my result by 0, which is not what I want. So all I need to do is take this button and put it through a NotGate. A NotGate is a Boolean operator which flips the Boolean. So false, not false equals true, and not true equals false. So we plug that into our B, and then there we go. So whenever the simulation is running, we're going to get a value out of there. So you can see now when I hit this button and release it, it resets the points to 0, and then as soon as the simulation starts up again, the points move up, which is pretty sweet. Now we've got our simulation doing exactly what we want. And maybe at this point now I can go back and tweak some of the earlier results. So we can dynamically increase this this sort of portion of the spiral that we want to fill, and the reason we can do that is because it does not change the underlying structure of the geometry. It only changes where points are, which is all well and good to do. If we were to change the number of steps, we're going to begin to break the geometry. But that's not too much of an issue, because all you'd need to do is simply, like if you did want to up the resolution on this a little bit, we can just reset the simulation and we'll be good to go again. And you know what, maybe I'm thinking this culling pattern needs a bit more, or fewer points around the center. So I'll change that culling pattern, and there we go. I sort of didn't like how many points of influence there were around there. So I'm pretty happy with this at this stage. As you can see, if we look back, that's kind of what Frei Otto was doing with the German Pavillion. I was sort of looking at this back region over here, and sort of, okay, maybe the last thing, oh, there's two other things that I'll show you. We could put this through a Catmull-Clark subdivision, just so that we're getting a bit of a smoother result, which is always a bit nicer. You don't lose too much of that sort of peak information. And the other thing we could do actually is, instead of extracting this as a mesh, we could turn it back into a surface. So all we need to do is a surface from points, deconstruct this mesh over here. I might stop the simulation for now. And so this is our collection of points, and our U value is exactly the same as what our U value was for this mesh from points, which is this value here. So I'll just plug that in, and when I preview this off, now we're getting this really nice surface result. There we go. I think that looks pretty sweet. Now there was one more thing that I did want to do. Let me see if I can remember what that was. Oh yes. This is sort of just a an added little extra that I don't really think I've talked about before. But what we can do is using Kangaroo, and well, what we could do is we could sort of mess around with the length of all these individual curve elements a little bit. We can do that in a few ways. What I'm going to do is we have these curve lengths over here. So I'm going to get a remap numbers component. I'm also going to get a bounds component. So bounds is going to tell me the lowest and the highest value in this list, and I'm going to plug this into my source domain. My curve lengths are going to go into my value. So basically it's going to look at these numbers inside this domain, and it's going to reassign them to this 0 to 1 domain, which is all well and good. And then what I want to do is I want to reverse I want to reverse these numbers. So what I'm going to do is I'm going to do 1 minus x. I'll get rid of my y over here, and then I'm going to remap them again, but I'm going to remap them instead of from this source domain. I'm going to remap them from 0 to 1 back to this target domain. And so what this is basically doing is this is looking at our input mesh, wherever it is. I think it's over here. And so where the curves, you can see that some of these mesh edges are longer than others. And so what it's going to do is it's basically going to flip that around. So where there's a shorter edge, those are going to become the longer edges. And the longer edges are going to end up being the shorter edges, which is kind of I think it's a subtle sort of interesting way to manipulate the mesh data to give a slightly more interesting result. And then we could once again take this result over here and multiply it by this slider, and then when I set my simulation off again, I won't use the surface preview, I'll use the mesh preview, and okay, well I mean this is sort of straying a bit from what the intention was with the Frei Otto simulation, but it is just another sort of cool thing that you can do with these meshes. Oh, let me reset the simulation over here. Yeah, there we go. So now it's really pushing out inside these inner regions, which were quite small, and then it's sort of tightening up a little bit in these external ones over here, which were a bit longer. But like I said, we don't necessarily need to do that. That was just a little extra thing that I thought might be interesting. We'll put it back in tension, and yeah, there we go. This is a look at how we can create the German Pavillion by Frei Otto using Kangaroo to create tensile structures. I hope you enjoyed it.